To the last session today, high fidelity turbulence 1. We have 3 presentations today, and the first one is from Nasser Belmiloud.
Wow.
Sorry, you will pronounce it better. He will tell us better, more about his large-scale Eddy simulations.
Thank you very much for the introduction. So maybe we can skip the camera because we have some simulation and yeah, perfect. Let's go. So my name is Nasser. I'm doing research, but also some process and technology in Screen. So Screen is a semiconductor company, and I will explain why we are doing CFD in the semiconductor area. This work have been done with Mr. Sato, which was responsible of the software in Tokyo, and our CTO, Okuno, Mr. Okuno-san. Okay, so these are the outlines of my work. So I will do a brief introduction because people doesn't know our company, and but it will be really brief, and also the purpose of the work. Then the simulation challenges. We will focus on the mesh, the boundary condition, and some problem we faced with the finite volume scheme, especially the divergence scheme. And we will show why we choose LES and not RANS, even if we have low Reynolds number problem. Then I will show the nice correlation between simulation and experimental data. So I will show some PIV data and some, then we will explain the wave pattern dynamic at the interface air liquid. So why we want to do a CFD? The motivation is, you know, in the semiconductor industry, we follow the Moore's law, and we have to go really deep into the device size. We are now at 3 nanometers, and the design of the chip or the transistor is really challenging. We are now to have high aspect ratio, and we have to face many problems because of particle contamination, but also from pattern collapse. So what we want is to clean the what we call the wafer, so the silicon disk, without adding particle. We don't want to have watermark, because watermark, as you can see, they are the micrometer, so the circular white disk. It's a watermark, and it's problematic because it means that if you do a deposition step after that, it will not have the same properties. And also it will kill your transistor, and that means your chip will not work. So it's a yield killer. And then you have the pattern collapse. So it's a nanometric scale. And why we have pattern collapse is because we have a partial drying. So we have a capillary meniscus between the pillar, and then it creates collapse. So with the CFD, we want to understand the mass transfer, and this is a simulation challenge. So we have the liquid. So first we have a vertical dispense, which is a immense flow. We have submicron thin film. You will see that the film thickness will go below 100 micron with high vorticity. We have some phase at the air liquid, some waves, sorry. We want in the future to play with the viscosity and density, but we focus only on Newtonian fluid. The flow rate, and for the surface, so we work in rotation, so which is a spinner, okay, at high speed, 1000 RPM, and we will check the weighting properties, so different contact angle. And also what is important for us is at the edge of the disk, at the bevel, we want to check how the liquid behaves here. If there is some wraparound, that means the liquid will go below, or if there will be some film breakage and droplet generation. So the simulation. So here that's the mesh, the design of our system. So it looks easy. I mean, you have a disk, okay, about 340 millimeter. The standard size of a wafer in the semiconductor industry is 300 millimeter. So you have the cross section, and in the cross section, you have the nozzle injector. So the cross section show only a radius and it's a side view and only on the radius. The injector is a 4 millimeter, so it's a nozzle where we will inject the water. And then at the edge, we have a bevel. And you see the thickness of the disc and also the shape of the bevel. And we increase the density of the mesh at the bevel to be sure that we are, because the boundary conditions are quite challenging in this area. We have quite a lot of mesh. We have 26 million. And we have, for the boundary layer, we put 12 layers here. So now let's speak about the boundary conditions, which are not maybe easy to check. So we put some colors to distinguish. So you have in red the water inlet. So we put 2 liters per minute, which is a velocity about 2.6 meters per second. There is no rotation. Okay, it's a fixed dispense at the center. Then in green, you have the air inlet. So we are blowing some air at the same speed, 0.3. Typically, because in our machine, we work with chemical. And if you work with chemical, you have to add an exhaust. The yellow part is the rotating part, okay, which refers to the disc plus the bevel area. And in blue one, the small part is not rotating, just below. It's the support. And we have a pressure outlet just for the air, okay, to go outside the system, to close the system. Here, the contact angle, it will be 10 degrees. And we use OpenFOAM 2012, and we use LES. I will explain why LES and Smagorinsky. So the challenges are for the volume of fluid simulation with LES. So we have the opportunity to use a supercomputer at Osaka University with a lot of computing power. Here we will speak about one problem we face because we think it will be interesting for the community. It's about the divergence scheme. So why we have the problem? So when we use rounds, this is what we are facing. We are facing a lot of film breakage. And as you can see, the area, the bevel is wet before the area before. There is a problem of the liquid when it reaches the bevel of the wafer. So normally we shouldn't see a breakage of the film. What here the pictures, we compare rounds and LES. We have almost the same conditions, let's say, okay, to make it comparable. What we face is that with rounds, we have a huge speed. So the speed was too high compared to what we expected. And we have a lot of droplet generation with rounds, but not with LES. So LES was really fitting our problem. I will show you later some data. So here's an issue we had with the divergence scheme. So we had some problem of overshoot, and the overshoot of the divergence explain why we have some huge speed into our simulation. So what we found is we use the best in our case. I cannot show, but so the ideal case is a stepwise function in purple or pink, okay? And we want a function which is closer to this stepwise function, but no overshoot. As you can see, for example, the blue one, the linear one, and the upwind are not close, or they are creating overshoot, which is not wanted for our system. And the best function we found is a limited cubic, which is closest to the stepwise purple function. And when we do that, we could find that we have a realistic speed, okay, which is closer to the reality. And also we have the best accuracy. So that's why we use in our system the limited cubic one. Now, what is the difference between the previous and the new one is that the previous one was really smooth, and from time to time we have some high velocity outside of the wafer. We didn't mention here because it was too difficult. And also the pattern of the wave seems smoothened. When we do the new diversion scheme with the limited cubic, we can find a pattern on the wafer. This pattern at the beginning was really weird for us because we didn't expect such a pattern at low Reynolds. Secondly, we checked the literature and we found one paper from Lee and al. Who did LES on ANSYS, and they found the same pattern as we have. And they found they have also the same problem as us. They couldn't go to the SST K omega because the runs couldn't show with high quality and high accuracy the wave. It was smoothened, and also they go for the LES. So also we mentioned that it was with ANSYS, which is a commercial one, and we could reach the same level with OpenFOAM. Secondly, what you can see that the two pictures show the reality. Okay, one is smaller than the other one because we don't work with the same size of the disk is not the same size. We are working with a bigger area. So it means that we are quite confident in our simulation. Then what we wanted to check is to confirm our data with experimental data. So here you can see the thickness and the radial velocity in the simulation. You can see the wave generated. So you can see a spiral. And then you will see some what we call before the S-shaped wave. Finally, I will explain later that you have at the middle of the wafer, you have a high thickness, where the flow is almost laminar. Then you start to have a spiral because of Coriolis forces, and this then will collapse because of the Coriolis forces. So here now the experimental data. What we did, we check the part. It's not particle velocity because there is no tracer in these systems. It's by light, and we check the contrast, and we track the contrast here. And we could measure the map of the velocity ux and uy over the liquid air interface. So the blue, the dark blue data are the OpenFOAM one, and the light blue are the experimental data for the angular velocity. And you can see that there is a really nice correlation between the angular velocity and what we found in OpenFOAM. And the same for the radial speed, and the radial speed is almost constant for both cases. So there is a really nice agreement between the LES simulation and the experimental data. So we say, okay, now we are quite confident, but let's check other things in the simulation to be sure that we are not giving a wrong message. I mean, here we just check the velocity. So then we check the literature again to check the classical model. And so in blue, you have the data point from the simulation, okay? And in red, we have what we call the asymptotic model, which fits at from a mid-radius to the edge. And you have the Nusselt model, we fit only at the center. And in yellow, you have the Rossby number, and you can see that the Rossby number is balanced after, for example, 50 millimeter. It means that the inertial force and Coriolis force are balanced somehow. So now we want to be sure that the conservation of the flow rate is verified along the radius. So we just check with this small sketch. You can see that the film, the liquid thickness is decreasing with time and the radius. It means that the flow speed has to accelerate. So we want to check if we have this relation that the flow rate, that the product of the radius, the thickness, and the radial speed is constant over the wafer. And this is what we almost observe. You have a box plot on your right, and you can see that the average of the box plot of all the data points is equal to the inlet. Secondly, we check also the thickness against the product of the speed with the radial speed and the radius, and we found a really nice correlation. However, when the wave starts, we don't verify this, and we think it's because we have to integrate. We cannot do a simple product here. Now, the vorticity. So we have low Reynolds number, but when we check the vorticity, we have a really high vorticity. So we couldn't understand at the beginning why we have high vorticity. One thing is, here you can see the vorticity against the thickness of the film. And you can see that when the film thickness reach 100 micron, then there is a big jump in the vorticity. And if you look at the map, the magnitude of the vorticity, you can see the red area correspond to where the waves are. And what we assume finally is when you check the vorticity formula is that the speed at the edge is maximum because of you are at the edge of the wafer, of the spinning disk, okay? And the thickness is low, so Z is low. That means you are increasing the magnitude of the speed, but you are decreasing the thickness, and that's why we assume that you have a jump in the vorticity. So now we check what we call the shallow water wave. So here you have a movie of the thickness in purple, in blue that's the angular velocity, and in red that's in green that's the radial velocity. So as you can see, you start to have some big wave at the beginning about. So please be careful about the X scale and the Y scale; they are different. Okay. So I put some data, and you can see that the height of the wave is about 200 micron, but the baseline is 7 millimeter. Okay, it means you have a ratio about 5 between the height of the wave and the base of the wave. Then when you think about shallow water, you think about tsunami. So we were thinking about maybe we are in a tsunami case because we are creating wave and we are decreasing the depth of the liquid. But in terms of when you have a tsunami configuration, the wavelength at the center should be higher than the wavelength at the edge. The wavelength at the center should be lower than the wave at the edge, and this is the opposite that we observe. So we are not in a tsunami case, and we are facing what we are for us in a similar case that a falling down film under gravity. How it works? So we found a similar case in literature. So the wave packets are initiated, and it's because of Coriolis forces. Then you have what we call the bow wave accumulation, which is finally a coalescence of the wave. And then you start to have some big wave because of this coalescence. They come together to create a bigger wave. And then this wave will collapse under the action of centrifugal and Coriolis forces. So now we did some, we say, okay, we are quite confident in our OpenFOAM code. So let's try some, not Lagrangian, but some analytical solution to detect the spiral shape of the wave. So we solved this equation. I just put the math here. So we solved this equation because it was not reported. And so here, I mean, we're solving the complex area. And if you want the coordinate, you just have to put the real part for X and the imaginary part of Y, and you do a parametric curve. And this is what you have in the red dot here. So the green line is the wafer, so the disk bevel, so the limit of the disk. And in the red part is the trajectory of one particle, and with the speed. And you can see that there is a nice correlation between the spiral in red and the pattern we have on the wafer. So for inviscid flow rate, we assume that, I mean, we should see a minimum time about 0.06 seconds. But in our case, if you look at the simulation, the water will reach the edge of the wafer with a minimum time of 0.12 seconds, so double. So if we take this average of 1.3, because you double, so you decrease the velocity, you can reach a nice spiral. However, our model is currently the mass point model. Okay, the analytical one is overestimating the speed currently. So now I come almost to the end of my talk. So here, what you see is so in the problem in our simulation, we work at high rotation. We work at 1000 RPM. So it means that the wafer will do 10 degrees in less than 0.17 milliseconds. So we need a lot of time step to do a small duration of the film. And what we want to show here is that here on your left, that's the result from OpenFOAM. So static camera from outside. And then we put a small Python script and we put the camera moving together with the disk at the same speed. And what you see is that if you do the rotation coordinate camera, the fluid move slower. So it means that maybe it's easier for OpenFOAM to work in a rotating coordinate. And that's why we think, we're not sure, but the MRF could be really interesting for us. So summary of my talk is that despite low Reynolds number, we could see that the runs model couldn't work. And we have many problems of film breakage and a higher estimation of the speed, a too high estimation of the speed. The LES with OpenFOAM could fit for us. I mean, we are quite confident about our code because we have the data that confirms the simulation. And also it shows that OpenFOAM can do the job of ANSYS. We have an excellent agreement also with the experimental data for velocity and thickness, and also for the wave pattern we observed on the disk. The main conclusion will be, in terms of physics, is that the Coriolis and centrifugal forces are responsible of the thin film perturbation that create this wave at the interface. So the wave propagate, and then you have a capillary coalescence of the wave, and then they collapse at the edge of the wafer. And you have high vorticity because you reach a maximum speed at the edge where the thickness of the flow is lower. So future work is we need to find a balance between accuracy of wave pattern and the computational cost. So unfortunately for us, we cannot work with a hybrid model. We cannot use runs at the solid, liquid, and LES out, because we want also to check the solid liquid interface, because I show you that the pattern collapse are really interesting for us. So what we want to do next is to check the MRF. So by the way, I would like to thank the OpenFOAM committee and organizer, because the turbo machinery talk was really interesting, and we will continue to discuss on this topic. And now we want to track the air-liquid interface. We use inter-isoform, but we think maybe to use interform. But we want to be again more accurate on the liquid-air interface. And the next modeling will be the film breakage at the disk level, the heat transfer in the liquid, and the future work and the main will be to do the chemical interaction between the liquid and the disk surface. So last slide for the acknowledgement, because this work couldn't have been done by without the supercomputer from Osaka University, and we would like to thank them for the help and support. Thank you very much for your attention.
Well, thank you, Nasser. Now it's time for questions. Yes.
Thank you for the talk. Very cool simulations. I'm a little bit confused about this RANS and LES thing. So with LES, so do you actually resolve the turbulence then? Is there, or I realized you got bad results for the RANS, and then got better results for LES, and then it's on the same grid. But I'm a bit confused. So what changed, so to speak? I mean, did you actually change the turbulence modeling regime? Did you have fluctuations in the LES, let's say?
So first of all, for us was so the question was, can you repeat the question? Because I have to repeat to the audience.
Okay, I guess in short, do you have a resolved turbulence spectrum in your LES?
Okay, so no, and I will say why. Because for us, we work in low Reynolds number. So we didn't expect turbulence at all.
Okay.
So for us,
why did you put RANS?
That's why at the beginning we put RANS, because we wanted high accuracy simulation, okay? And we didn't care about the turbulence. Because for us, our system, but this is what we thought. When you do the calculation, the Reynolds number is low, so why we should go to LES? But in reality, RANS is not working. We have to do LES, so we have some turbulence, and it's mostly at the edge of the wafer, and we think this turbulence is resulting because of thin film. So really, you are decreasing your liquid thickness, but you are increasing your speed. Sincerely, for us, it's something we still have to investigate, because it's not clear where the turbulence is coming from. We just know that if you do LES, it's closer to the reality, and even there are some paper on it, and they didn't find the root cause the main
Try
assumption.
to just not have a turbulence model, just set it to laminar.
Let's try. I mean,
Sorry.
we can try. I mean, we are open to suggestion, but I mean, definitely it works. So you can see that the flow is not laminar. You see the wave. You see the flow is not laminar at all. We think it's because of the wave.
Maybe related to that, did you check the mesh? So did you try the final mesh?
Yeah, so we increase step by step the number of mesh, and currently it's more stable with the mesh number we have currently, 25 millions, around 25 millions.
Okay.
Are you using any warm model for LEF or you run models of LEF?
Warm model?
For
Wall
LEF?
model.
Can you explain, for example?
Because if you run with a Husserl mesh, usually people will use warm model for the near the boundary layer, so that you don't need to use such a very fine mesh.
So basically, wall functions.
Warm function, yeah.
I don't think so. I have to double check with engineer.
Yes, maybe if you check maybe another turbulence model, for example, in our research center, we are also making modeling of rotational flow with compressors, yes? And we used to do it with the K omega SST until we found the Ray-Agar-Ball turbulence model, for example, which is way more efficient per se, yes, because it's in a relation between the K and the omega parameters, and it has given us less good results. Have you tried maybe making a test with another turbulence model?
No. So this work has been done in 1 year. So that's why less than 1 year. That's why we came here to we are open for suggestions. Yeah.
We have also some issues with the K omega SST
Yeah.
in our simulation. So my work, for example, the Ray-Agar-Ball turbulence model is quite new, but it has given us good results for rotational modeling.
Okay. Yeah. Thank you for your recommendations.
Okay, and 2 more questions from the chat. So, did you try to solve with the cyclic boundary conditions and not rotate? And did you check why runs didn't work?
Yeah. So I think the first question, I mean, so you mean a periodical boundary. So
Yeah.
instead of a disk, I will put a pi.
Yeah.
Yeah, we try, but I mean, we have other cases where but unfortunately we couldn't present here, where we are breaking the symmetry of the flow, and we cannot work with a pi. For example, the nozzle is not vertical; it will be an angular nozzle, and here you break the symmetry, and you cannot work with a pi with periodical boundary conditions.
Oh, that's good. And well, runs you also didn't check. Why didn't it work?
So runs for us, I mean, we think that it doesn't work because somehow we are in a high turbulence regime, but we have to investigate why. We almost think that is because of the wave regime.
Good. So let's.
Thank you very much. Again, I'm Joshua Brinkerhoff from University of British Columbia in Canada. I'm presenting work on behalf of my PhD student, Shahab Zeraati Dizjeh. As was mentioned, we're going to be focusing on numerical investigations using large eddy simulation of turbulent heat transfer enhancement in modified internal tube profiles, essentially a circular tube, circular pipe, where we add on additional profiles to enhance convection heat transfer. The motivation for this work is steam cracking process in ethylene production. Steam cracking is a chemical process used to convert ethane into light olefins, including ethylene. And the process involves putting ethane gas and steam in large tubes in a large furnace. The furnace heats up the tubes from the outside, and the chemical reaction occurs for the steam cracking process. But it's a very energy intensive process and also a very carbon emissions intensive process, whereby 200 million tons of CO2 per year can be attributed to the ethane or light olefin production process. And this motivates methods for investigating ways in which energy can be saved. Secondarily, the steam cracking process also has the resultant effect of producing amorphous carbon coke, and that coke can deposit on the interior wall of your steam cracking furnace pipes. That creates maintenance problems, additional pressure losses, and eventually degrades the chemical reactions that are occurring inside the pipe. And so the project investigation here is ways in which we can improve the heat transfer. And by improving the heat transfer, the gas layer near the surface of the pipe is hotter. That reduces the production of coke, and we can reduce the amount of energy that's needed to run the furnace in the first place. Just to comment about the conditions, the Reynolds number in these pipe flows would be on the order of 55,000 to 200,000 based on the bulk velocity and the pipe diameter. The Prandtl number would be slightly less than 1. Oh, my laser is not very visible. The flow is fairly fast, but the Mach numbers are still on the order of subsonic, maybe slightly above Mach 0.3, but not a lot. And so we can take advantage of the assumption that the flow is likely incompressible, although it's very hot. The gas inlet temperature is going to be on the order of 600 or 700 degrees Celsius, whereas the wall temperature is going to be on the order of 1,000 degrees Celsius. The flow is not at very high pressure. Atmospheric pressure can be a reasonable assumption. And so in order to enhance heat transfer, we can categorize different methods under active and passive. And active methods require an additional power source, whereas passive methods use special surface treatments to augment the heat transfer, but without an additional expenditure of energy. And so one could use fins or inserts or twisted strips or structures or dimples inserted into the pipe to enhance the turbulent convection. And that's great, but the drawback is oftentimes enhancing heat transfer also enhances hydraulic losses. And we have an additional pressure loss and as a result, entropy generation and loss of useful mechanical work. And so what we want is we want to enhance heat transfer without increasing the friction factor for the pipe. And we can categorize different techniques in a so-called evaluation plot where we plot the log of the ratio of the Nusselt number of a modified tube to the non-modified tube versus the log of the ratio of the friction factor of the modified tube to the non-modified tube. And this is what we refer to as an evaluation plot. And poorly done heat transfer will lie in regions 1 or 2, where the enhancement is less than the increase in pumping power. You could get as much increase just by pumping the fluid faster. Region 2 is enhancement that can be obtained with identical pressure drop. Both of those are non-desirable, whereas region 3 and 4, the enhancement is less than the increase in the friction loss ratio. And then in region 4, the enhancement is greater than the increase in the friction loss ratio. And so what we would like to have is inserting additional surface profiles that enhance heat and enhance the turbulent convection, ideally in region number 4. So we did a literature survey. We looked at all kinds of different materials, transverse repeated ribs, perforated tips, tapes, wire coils, etc., for a broad range of Reynolds numbers. And we compared them all in the basis of this evaluation plot. And this helped us to identify which techniques we wanted to adopt and study for our project. And so we selected a comment here is that the literature lacks adequate resolution of turbulence data. And so there'll be an experiment. We have different types of heat transfer enhancement techniques, and they produce an evaluation plot like this, or they give data that we can use to generate an evaluation plot. But then there's no answer to the question, why does that particular structure behave in that way? Why does it enhance heat transfer? Why does it promote additional friction factor? Those kinds of detailed questions are not clear. And that makes it hard to make design improvements and design optimizations and to make recommendations to manufacturers as to how they can modify these internal structures. And so that motivated us to do a more in-depth study where we can look at the physical processes in the turbulent flow that enhance the heat transfer in this highly turbulent arrangement. And that helps us to give guidance to industry. So the methodology for this work is, again, large eddy simulation of 6 different profiles, 2 smooth wall profiles, one for validation against benchmark data occurring at normal, like room temperature conditions. The other one, again, occurring at realistic conditions for the ethylene production furnaces. And then 4 textured profiles with ellipsoidal elements that are protruding inside to the tube, coils along the inside of the tube, and wavy or spiraled corrugations in the tube, which might resemble rifling inside the interior of a rifle barrel. The flow properties are given here. You can't really see my cursor very well, but the key point is all of these are simulated at a Reynolds number of 90,000 based off of the pipe diameter, inner diameter, and the mean bulk velocity. Mach numbers for the conditions under the realistic ethylene production furnaces is around Mach 0.25. And then the Richardson number also is given there. The Richardson's number is relatively low, from which we can deduce that buoyancy forces are not going to be tremendously important. And from there, we also can see that the amount that the fluid heats up across our domain is relatively small. And so for the purposes of simplicity and also numerical stability, we are making the assumption that the fluid properties can be assumed to be constant. And that's not correct, really, in real life, but there's not a significant range of temperatures as the fluid moves through the domain. And so for our purposes, we treat the fluid as a composite fluid with average properties for the average of the temperatures between the wall and the entrance of the fluid. The methodology is given here. So again, we're using buoyant Boisenesque pimple foam, but we're dropping the buoyant part. We're not considering gravity in the problem. We're using this because it's convenient that the temperature is already present in that solver. It's a transient incompressible flow solver with transient convective turbulent flows with a Newtonian fluid. It uses a merged piezo simple algorithm, although we don't use tremendous large time steps, so we could just get away with a normal piezo algorithm. That's what we're doing, and the buoyancy forces are neglected. In our case, because of the very high Reynolds number, we're using a subgrid model and wall attached linearity viscosity model, but we're not using wall functions or modeling of the wall because of the fact that we have these structures on the wall, and those are modifying the turbulence, modifying the heat transfer, and obviously a wall model is not built to account for those things. So we're resolving the wall. This is a picture of the grids that we've done. We have done quite an extensive amount of grid independence study, but only for the smooth wall grid because it's very time consuming and challenging to build the grids for the textured surfaces. The information about the grids given in the top corner, you'll see that the smooth wall grids use 24 million elements and the textured grids use between 50 and 78 million elements. The care was given to the element size near the wall to ensure that we get adequate resolution of the sublayer, the viscous sublayer near the wall, as well as the wakes of these structures, et cetera. We wanted to make sure that those were adequately resolved. The boundary conditions employ a fixed wall temperature and a no-slip condition for the pipe surface. There's a zero gradient at the inlet and the outlet. We are using cyclic conditions, so we have a periodic domain. And that means the initialization is quite careful. We have to do it carefully. And the way that we initialize the flow is like this. We start off with a uniform inlet velocity and a uniform inlet temperature, and we allow the flow to develop with periodic boundary conditions, which means that the velocity profile is gradually developed and it becomes less uniform, and the turbulent profile is gradually achieved as the flow cycles and cycles and cycles through this domain. Then we allow for this time-varying turbulent inlet condition to be mapped back at the inlet of at the beginning of each subsequent step by projecting the velocity and the temperature fields from the previous time step near the outlet plane to the inlet plane. And that allows for the turbulence and the temperature field to evolve. But if we keep on doing that, then our temperature is going to continually increase and increase and increase as the temperature field is heated by the wall. And so once the temperature condition has reached a thermally developed state, we stop mapping the temperature and we only map the velocity. So we have the turbulent structures being carried through the domain as if the domain is infinitely long, but then we're looking at the temperature development as if we're focusing on this particular region of the turbulent pipe. And so this way we don't have to simulate a very, very long turbulent pipe. We get the effect of the very long turbulent pipe on the turbulence itself. And then the temperature field we're looking at is evolving from whatever the temperature field is at this particular point. Okay, so that means the temperature field, we get the effect of the turbulence as well as the effect of its development, but then not having the temperature continuously being developed. Okay, so that's a little bit of an unusual thing. To validate the approach, we did an isothermal simulation and compared it against DNS results from Chin et al., where we very good match to the mean velocity profile. So the lines are ours, the symbols are from Chin et al., as well as a reasonably good match of the Reynolds stresses. This is the axial stress, the azimuthal stress, and the radial stress. We didn't have space on the curve to show the shear stresses, but the agreement was about the same. In terms of bulk quantities, our friction velocity matched within 3%, the friction factor 8%, and the Nusselt number within 6%, which at this Reynolds number was intolerable for us. Again, it's quite a high Reynolds number. If we look in terms of the friction velocity, RE tau is near to 3,000. That's a very high Reynolds number. All right, so just to kind of show overall, how did our treatments, our heat transfer enhancement treatments fare? Not tremendously good for some of them. For example, this spiral corrugations is in region 1, the coil insert in region 2, but the ellipsoidal elements at least have some promise, and depending on how closely spaced the elements are. So we have 2 element cases, one in which the elements are spaced 2 times further apart or closer than the other one. So E1 is the one where the elements are more closely together. E2 is where they're more further apart. And we can see in terms of improvement in heat transfer, E1 is better, but it also has more friction loss. In that case, E2 is better. And so now, which one should we choose? Let's look into the details in more description. To start off, let's just investigate the instantaneous velocity field. So I'm not showing the smooth wall case because it's relatively not so interesting, but for the textured cases, what we see in all of them is this is the instantaneous velocity. The textures themselves modify the flow and interrupt the turbulence in particular ways. So here we see the wake that's created downstream of the spiral coil. Even more so, we can see the wake that's created with even reverse flow in the backs of the ellipsoidal elements, and the strength of that wake being strongly dependent on the spacing of those elements. If we look at the turbulence field, and here I'm looking at turbulence by calculating the turbulence kinetic energy and then integrating that over the entire volume and then dividing by the volume. So now I have the kind of volumetrically averaged turbulence kinetic energy, and then I plot this against, for all of my cases, against the smooth wall case. So here we see 1.84 times more amount of turbulence, if you want to think of the value here of K star representing the integrated amount of turbulence you have in your volume. And so we can see that the cases that have the highest heat transfer enhancement also are generally triggering the most amount of increase in turbulence, but that's not always the case because E1, E2, so this second ellipsoidal ones with the elements spaced further apart, also has a very good improvement in heat transfer, but not necessarily a large increase in the turbulence. And that's because only increasing the turbulence, as we will show in a minute, doesn't necessarily improve the heat transfer. Only certain parts of the turbulence help the heat transfer. This is showing heat transfer enhancement in the context of the contours of Nusselt number ratio. So it's the Nusselt number for the local flow simulation divided by the average Nusselt number in the non-textured case. That's what this ratio represents. And it's colored by this ratio. And then over here in the histogram, we have the representative area fitting within a certain band of Nusselt number ratio. So the dark green represents Nusselt numbers that are 90% of the baseline. The light green represents between 90 and 100% of the baseline. The yellow is between 100% and 110%. The orange 110 and 200%, and the red more than 200%. So obviously we would like the bars to be all red. We would like all of our flow to have a significant increase in the heat transfer, but that's not the case. Some places the heat transfer is augmented a little bit. Some places the heat transfer is degraded. Those are the green bars. And the location of where the heat transfer is augmented and degraded is shown in these contours. So if we look at the spiral, we see on the leading edge of the spiral, significant augmentation of the heat transfer, but then in the wake of the spiral, a degradation in the green. And then that's because of flow separation downstream of the spiral. But when the flow reattaches, we can see this kind of more shaded region labeled C, where we have, again, recovery of heat transfer augmentation and increase. Similar things are observed in the corrugated spiral case, with the E representing the degradation of heat transfer enhancement as a result of boundary layer separation downstream of the coils. In the case of the ellipsoidal elements, things are a little bit more complicated. We have an increase in the heat transfer on the leading edge because of the impingement, the high velocity that's present there. We have an augmentation in heat transfer around the surface, which we can attribute to a horseshoe or a necklace type vortex around the structure of the element. And then also an increase in the wake, although a small decrease in the immediate downstream portion of the element itself. Between the element rows, we have a degradation in the heat transfer overall. And this was kind of unexpected. And one takeaway from this is, what if the elements were staggered, not all aligned? That might improve things a bit better. Let's focus in a little bit more on the heat transfer enhancement related to the steady, quasi-steady turbulent structures that are present there. So this is isocontours of Q criterion, but it's Q criterion based on the mean velocity. Because it's a very turbulent flow, we have coherent structures that are coming in and out of the flow all the time. I want to know, well, what are the structures that are stuck onto my textures that are present and on a time averaged quasi-steady sense, adding to the additional heat transfer. And so that's why the mean velocity is appropriate for these Q criterion. And again, what we see is the enhancement in heat transfer that we saw on the previous slide can be easily linked to these kind of quasi-steady turbulent structures. There's no one coherent vortex that looks like this, but if I take the Q criterion or look at the coherent vortical structures that would be the amalgamation of my time averaged flow, this is what I see. And so on a whole, the coherent structures that Okay, so again, to highlight the importance that it's not turbulence that enhances heat transfer, it's the right kind of turbulence. And the ISO contours that show these different values of this correlation highlight the importance of those particular correlations to illustrate why the hemispherical elements are augmenting the turbulence in the way that we saw. Okay, now again, we want to investigate the effect of pressure losses. In a smooth wall pipe, there's only skin friction to account for the pressure. But when you have textures, they stick out and they introduce additional form drag. And so what we've shown here in color is a drag ratio, or what we call drag ratio, where we have the ratio of the skin friction drag to the, what is C tau again? C tau is the total amount of drag, skin friction drag in the non-profiled case. So we normalize the drag associated with the skin friction in the profiled case, as well as the projection of the static pressure in the axial direction. That corresponds to the, if you like, on an airplane, it would be the, well, the form drag, essentially, the forces that are in the axial direction by these little structures that are sticking up and being out of the way. You stick your hand out the window, that's the pressure you would feel. And the bars show the relative contributions of the skin friction and the form drag. And so what we see is the different ellipsoidal elements overall contribute quite significantly to the form drag. All of them increase the skin friction drag. Some of them increase the skin friction drag quite marginally, others quite a bit more. And we see it's their relative interplay of both of these that are important in the context of friction enhancement, which we want to avoid. The other thing we can comment on is entropy generation. Entropy, again, represents the loss of useful mechanical work. And it can occur through, of course, heat transfer across a finite temperature difference, as well as irreversibilities. In our case, primarily irreversibilities associated with turbulence. And the ratio of the total entropy production from heat transfer divided by the total entropy production overall is called the Bayesian number. And what we show here is a plot of Bayesian number in the green to purple scale, as well as a plot of the entropy production normalized by the entropy production in the baseline case in the green to the blue to red scale for the different cases. And we wanted to have a case that increases the heat transfer, but also minimizes the entropy generation. And so we just calculated a performance parameter that's the ratio, the inverse of our the inverse of our entropy production ratio times the Nusselt number ratio. Okay, so the bigger the number of capital E, the better our case is in terms of enhancing the overall heat transfer with a minimum in entropy production. And again, we can see that the case E1 with the most closely spaced ellipsoidal elements had the highest heat transfer, but it also had quite a bit of loss. And so in terms of this E performance parameter, it's the more broadly spaced ellipsoidal elements that is maybe the best solution of what we saw, which is kind of counterintuitive and not what we would get if we looked only at the evaluation plot. Okay, so to conclude, there's a lot of text here. Overall, what we wanted to know is how does augmenting the turbulence in a real-life industrial application increase or improve the heat transfer enhancement, and at what cost in terms of friction increase and entropy production increase. And we looked at different profiles, and what we saw is some profiles work better than others. And the reason why they do that is because they trigger strong radial fluctuations that act against a strong mean radial temperature gradient. And elements that do that work well. Elements that increase the turbulence just kind of arbitrarily and in an isotropic manner don't necessarily result in a high amount of heat transfer and may increase unnecessarily to the overall irreversibilities and entropy production, and as a result, loss in the system. This is just a test of 4 textures. One could use the highlighted, the knowledge gained from these textures to imagine other ways of building textures better. Very, very low hanging fruit is having the textures staggered to one another. Thank you very much.
Very nice presentation. Let's hear the questions now. Yeah, go ahead.
I was wondering, like, for your method to control the bulk temperature, I was wondering if you consider to use like a forcing term to the specific scalar equation to control the bulk temperature in the channel instead of on the pipe, instead of using your approach of mapping and stopping it.
Yeah, that would be a little less late. So the question was, why didn't I just introduce a forcing term or a sponge layer at the end that would force my temperature field to go back to a desired target temperature field? That would have been a less labor intensive way of doing it. I don't think it would change the results. It would have been a smarter way. But, you know, with graduate students, oftentimes we prioritize getting things done rather than getting them done in the right way.
Sorry, I got the same question. So when you look at I'm just interested because you're comparing like I was thinking in terms of the wall heat flux around the entire tube itself. But have you looked at like a globally spatial average quantity and how does that compare to the smooth case? Because there is local heat enhancement due to those textured surfaces.
Yes.
But then in a global sense,
yes,
is it better than the smooth pie or?
Well, that's what we showed in our evaluation plot at the early. So if I go all the way back to the beginning, this evaluation plot here does give a ratio of the globally averaged heat transfer rate, Nusselt number, to the baseline Nusselt number. And all of them are above 1, which means they all increase the heat transfer enhancement, but they also all increase the friction. And so we want ones that increase the heat transfer rate globally without increasing the friction losses globally too much. And that was kind of the objective. We know that we can increase the heat transfer. It's not hard, but doing it without getting a big penalty, that's where it's hard. And then understanding what causes what was the whole motivation in this study. Thank you.
Okay, there was another question.
Thank you, Professor. So the different designs of the tubes that you analyzed, they were like already made, right?
Some of them are used commercially. Others are ideas that we had and we wanted to put in. All of them were with an eye towards manufacturing. We could imagine really complicated shapes, but they needed to be manufactured in a particular way. The company that we were working with, its expertise is not so much on building these furnace tubes, but they develop a special coating. And that coating is a special catalytic layer that reduces the coking. And what their kind of benefit to the industry is we can provide you a coat with a special augmented shape of these structures and things. So not only are we reducing the coking problem through the catalytic chemical special sauce that we've invented, but we also improve your heat transfer rate and reduce your energy expenditures, et cetera. So that was the motivation here.
And what about I saw that, I don't remember the number of the slide, but you make an analysis of the kinetic energy performance along the different designs, right? What about the vorticity magnitude? Do you think is that necessary to compare or no?
We looked at vorticity. We looked at vorticity transport equation. We looked at turbulence kinetic energy transport equations, all of these things. What we found was the most explanatory was this correlation term between the radial velocity fluctuations and the mean temperature gradient in the radial direction. Nothing else was quite as clear in explaining the interaction between the heat transfer and the turbulence.
Thank you.
All right, well.
Hey, can I have a question?
Yes, later on, sorry. We have 2 here in the row.
Okay.
Yeah, just a quick one. Yeah, thanks for doing your analysis. I was just wondering if you're going to put this data online anywhere. I know a lot of people do a lot of things with such finely resolved simulations.
For the right price. No, of course, of course. It'll only take a beer later on.
The question was, is it going to be online anytime soon?
Yes.
Yes, and One more.
Yeah, I was wondering, so I guess these elements, they can be seen somehow as roughness, right?
Yes.
In a way, did you see like in what regime you are in terms of the roughness? Is like, or
Yeah, these would be big roughness elements. Their height in terms of the Y plus for all of them is 100. So they stick out well beyond the viscous sublayer into the, well, actually beyond the overlap region into the log-law region. So
if you plot like log-web plots, the proper scaling would be not the inner units, but let's say the height, some equivalent height of the roughness.
yeah, that's right. We did use inner units for most of the normalizations, and that's just because of the kind of established procedures in pipe turbulent flows.
Okay. What was the question from the Zoom audience?
Yeah, I was just wondering, how did you come up with the design of these ribs? Did you perform some kind of optimization study beforehand, or?
The shape of the coil was from literature. The spiral grooves also came from literature. And the idea for ellipsoidal elements came from literature. The specific spacing and so on, also we selected on the basis of the literature survey that we did at the very beginning. I don't know whether the specific, pitch and so on properties that we selected are present in the literature that we saw here, but at least it was motivated from what we saw already in the literature.
Mm-hmm. Yeah, I was wondering if some kind of steady RANS simulation at least gives similar trends. Of course, not with the same accuracy, but at least produce the similar trends. Maybe it's possible to perform some kind of optimization to push it towards the region 4.
It's a good question. I would have at least one reservation with RANS, and that is you have to resolve the wall or you have to use a wall model. If you resolve the wall, the cost is going to be very high. And if you use a wall model, you're not going to see the effect that these things have in the inner layer of the flow. And so I think it may be possible, but I have my doubts as to how accurate it could be. But good point. Thank you.
Thank you.
Thank you. So again, my name is Joshua Brinkerhoff. I'm presenting the work on behalf of my postdoc fellow, Umair Ismail, and the work is boundary layer transition on a flat plate with an elliptic leading edge subjected to an accelerating and decelerating free stream. The motivation for this work is transition as it pertains to gas turbine aerodynamics. Obviously, as we understand, gas turbines consist of multiple rows of turbine machines. There's a compressor, there's a turbine section. There's actually multiple stages of these compressors and turbines. And in the context of the low pressure turbine, the transition has a significant impact because in cruise conditions, the flow actually is operating at relatively low Reynolds numbers. The flow generally has a tendency to separate from the suction surface and undergo separated flow transition. And so we study this, and oftentimes we study it using direct numerical simulation where we make a very gross approximation of the inlet conditions of the flow. Generally, in the context of kind of fundamental DNS simulations, we impose a pressure gradient on a flat plate. And the flat plate acts like a proxy for our blade suction surface. And the pressure gradient is imposed either using a boundary condition or a contoured wall. And that gives the representative conditions, and we can add turbulence, we can do all kinds of things to also look at the transition in a more realistic way. But the simplification that's made is we assume that the flow entering the flow has some kind of laminar condition and it reaches the test surface as a kind of sharp discontinuity of the flow. And the actual fact, the leading edge of the blade, of course, has a finite bluntness. And that is oftentimes neglected, especially in the more fundamental types of studies for boundary layer transition. And so within this project, what we wanted to understand is to represent realistic free stream conditions and realistic boundary shapes, and particularly focus on the effect of the blunt leading edge on transition in a flat plate with an accelerating, decelerating free surface that has conditions representative of a low pressure turbine blade. So this is what my geometry looks like. I have a flat surface On top of my flat surface, I have a contoured ceiling that imposes a accelerating, decelerating pressure field that represents the suction surface of a low pressure turbine blade. But then at the front of my test surface, I have an elliptic leading edge. And the geometry of my elliptic leading edge is given. It has a major to minor axis ratio of 2 or 4, I forget. And I'm doing a DNS. And so being a DNS, I don't need to worry about very much. I just solve the Navier-Stokes equations with no modeling assumptions. And so I can use IcoFoam, probably the simplest of the OpenFOAM solvers. And the simplicity is in the solver, and the complexity is in the physics that the solver is able to resolve. We use piso and central differencing, so we have second order spatial discretization and second order temporal discretization as well. The resolution of our grid in all respects is less than 11 wall units. Near the surface of the wall, a minimum Y plus is 0.5, and our time time step size in wall units is 0.05. Kind of the rule of thumb for DNS is that it should be less than 0.2, so we satisfy that. The time step size here is imposed by the stability constraint of the solver. We wanted to validate our results, but there aren't experimental measurements of this configuration. So we used a zero pressure gradient turbulent boundary layer at a fixed Reynolds number of RE tau 180. And our argument is the flow processes that are occurring in a zero pressure gradient turbulent boundary layer in terms of the sweep and ejection processes occurring in the turbulent boundary layer are representative of what we see. And so it may be suitable to validate our solver, or at least the solution approach, using a companion DNS of a zero pressure gradient turbulent boundary layer. So that's what we've done. These symbols correspond to the DNS data of Bob Moser, 1999, at that same Reynolds number. And the lines correspond to our DNS data. We see perfect match in almost all respects in the mean velocity, turbulence stresses, and also budgets of the turbulence kinetic energy. And that's saying something considering the high order moments that are present in our turbulence kinetic energy budgets. So with that to say, if someone tells you you can't use OpenFOAM for DNS, give them my email. I would beg to differ. So now we have the reference length and the mean flow and the free stream description of the flow. So the side, what's the side? Your left is the mean velocity in green and the skin friction in red. One notices that near the leading edge, the skin friction drops to negative and then becomes positive again. That's an indication of boundary layer separation occurring near the leading edge of our flow. The flow is accelerated to a certain peak, which occurs near 60% of the length of our plate. And then it's decelerated again. And again, this is an indication of the imposed pressure gradient where we have the flow accelerating and then decelerating. But then near the leading edge, we have this kind of specialized the artifact of what's going on right near the blunt leading edge. The momentum thickness in red is shown here. The Reynolds number based on the momentum thickness in blue is also shown. And then the shape factor H is shown in green. What you'll notice is the shape factor initially near the leading edge is very, very high, indicative of the flow being having to separated boundary layer. Our Reynolds number based on theta at that point reaches close to 420, which is sufficient for transition to occur quite rapidly. And you'll notice that the momentum thickness grows very aggressively and our shape factor drops very aggressively, which suggests there's a rapid transition that occurs right near that leading edge. The far parameter is the acceleration parameter, K. The acceleration parameter is a measure of the strength of the favorable pressure gradient. And the bounds indicated by the dashed line, K of 5.2 times 10 to the negative 6, is the bound of acceleration parameter where above which the relaminarization is expected. And we can see that we are slightly below that. And so the acceleration that's imposed by our favorable pressure gradient is strong enough to diminish the turbulence, but not completely relaminarize the flow. And that leads to some interesting observations. To start off, I want to categorize the flow into 3 zones. The first zone is right near the leading edge, where we see a laminar separation bubble. The second zone is in the favorable pressure gradient region, where there's relatively strong mean flow acceleration. And the third zone is after the suction peak, where we have an adverse pressure gradient and relatively strong mean flow deceleration. Let's focus in on zone 1. So here we have 3 animations that show on the top left the instantaneous velocity. And you see, again, this separated dead air region where your boundary layer separates from the flow. If you look on the bottom left, there's contours of the span-wise vorticity. And we see the shear layer there rolling up, unsteady, amplification of span-wise vorticity that accumulates in the streamwise direction and then rolls up. We see a fairly distinct Kelvin-Helmholtz instability and these kind of distinct span-wise rollers leading to a vortex strain that then undergoes 3-dimensional amplification and breakdown to turbulence. And if we look at isocontours of Q criterion on the far right side, that's also what we can see. The span-wise homogeneity of these disturbances is sometimes clear and sometimes less clear. And what we actually are seeing is the inviscid instability interacting with a viscous instability in a different location of the flow that sometimes makes the inviscid instability a little bit less pronounced. Then the roll-up of those structures occurs very rapidly. We have hairpin vortices that spawn subsequent hairpin vortices that spawn subsequent hairpin vortices, and we'll see this has a significant impact on the near-wall momentum exchange and creation of turbulence downstream, really close to this leading edge. So even at this point, we can say the importance of resolving the blunt leading edge is quite significant, and neglecting that might have deleterious consequences. A more focused view of the instability in that separated shear layer is shown here on the left. Again, this is the fluctuating streamwise velocity animation. We see high and low speed fluctuations developing in the braid region between these shed spanwise structures. We have violent eruptions with negative streamwise velocity fluctuation, accompanied by significant sweeps from a layer above with positive streamwise velocity fluctuation motions. And this leads to a rapid breakdown in small scale and the creation of 3D structures. On the left-hand side, we kind of plot a time story in steady sense, where we show the kind of evolution of these low speed negative streamwise velocity fluctuation from this instant to this instant, to this instant, to this instant. And what we see there is in addition to this flapping of the shear layer in the red, we have this amplification of negative streamwise velocity fluctuation that occurs really near to the wall. And what we think this is possibly the presence of an absolute instability that's triggered by the reverse flow, strong amplification of viscous disturbances in that reverse flow region, where we have this absolute instability that's more or less stuck in place and amplifies not spatially as much as it amplifies temporally. And then when it becomes strong enough, interacting with the flow in between the braids of these shed inviscid structures. So again, interaction between viscous and inviscid instabilities that promote the roll-up and break down to 3D structures downstream of the separation in the detached shear layer. Okay, so to give kind of a more full explanation here, we have probed points 1, 2, 3, 4 in these different locations. We see probed point number 2, which is in the middle of the shear layer, catches the flapping very nicely of that separated shear layer. And it has a peak, that most pronounced peak at between 140 and 220 hertz, which is what we expect in the context of Kelvin-Helmholtz instability mechanism. It's also present in 1, which is slightly upstream. But what's not as present is that second peak at the higher frequency. And that second peak at the higher frequency is more representative of what we think is a viscous instability, absolute mode, that's developing nearer to the ground, near to the wall. On the far right-hand side, the location 3 and 4, we begin to see the development of a inertial scale range where it matches the Kolmogorov -5/3 range, although over a relatively narrow band. but this is an indication of the development of developed turbulent scales. We have a breakdown and an exchange of energy across a broader range of scales. So the transition that occurs near the leading edge triggers the development of small scale turbulence, but it doesn't fully develop because the small scale turbulence that's there, it doesn't have a chance to deposit much of its energy to the smaller scales before the the favorable pressure gradient comes in and kind of slows everything down. So let's move over to that region now into the view of the favorable pressure gradient region. So this is the plot of our mean velocity at different locations along mean velocity profile in wall units at different positions along our favorable pressure gradient. With the dots represents the law of the wall. And what we can see is that as we increasingly develop more and more further along the favorable pressure gradient, we get further and further away from this kind of law of the wall turbulent profile. What we see is that our RMS fluctuations don't really go away. So the RMS fluctuations still stay put, but our shear stresses drop way down. So what we see is the turbulence that's created downstream of our separation bubble, relatively three-dimensional. Then it moves into this favorable pressure gradient region. The fluctuations that are longitudinal, the U prime fluctuations remain, but the U prime, V prime fluctuations get significantly down. And that's very interesting. So what we think are occurring is the favorable pressure gradient is essentially freezing the streaks that are created by the turbulence that was generated near the leading edge. The leading edge generates some turbulence. That turbulence is associated with longitudinal streaks with fluctuating streamwise velocity. Those streamwise velocity initially can generate cross-stream momentum exchange, strong Reynolds stresses, but then as our favorable pressure gradient it diminishes the ability for the turbulence to eject momentum normal to the wall, but the streaks are still there. So we still have strong longitudinal fluctuations, and you can see them here, but the wall normal fluctuations become significantly down. And this has been studied and observed before in favorable pressure gradients, and people call it the freezing or the frozen turbulence, insofar as the turbulence is not developing anymore. The wall normal momentum exchange, the Reynolds shear stresses are being diminished significantly, but the longitudinal stresses are still present. In other words, the streaks are there, but they just are stuck. They can't do the things that streaks want to do. They can't become unsteady and generate wall normal ejections or sweep motions in the boundary layer, because the adverse pressure, the favorable pressure gradient is just putting a lid on the party that the turbulence is wanting to have. Okay. And maybe topologically, what does this mean? Topologically, this means that the free stream pressure gradient is flattening our hairpin vortices. It breaks up their heads and it elongates their legs. And if I play the animation again, it becomes more clear, where we have creation of these hairpin structures in wave packets, and then their acceleration in the favorable pressure gradient region. And we see that the large hairpin structures with big heads, as they develop downstream, the red region, which represents the distance from the wall, is diminished, and the streamwise legs are stretched. That's another feature of the favorable pressure gradient accelerating the flow. You have a stretching of these legs, but without a concomitant increase in the wall normal velocity fluctuations. We could measure things about the streaks. So I've plotted here the mean streak spacing and the mean streak amplitude normalized in different ways. And the kind of takeaway message here is the streaks are there. They don't really become differently spaced. They stay more or less the same streak spacing. And the green represents normalized by the plate length. The red represents normalized by the local friction velocity. So in terms of their actual spacing, it's the green. They don't really change their spacing tremendously. And they don't really get much stronger. So normalized by the local velocity, it's the red, they actually become weaker. Normalized by the reference free stream velocity, the green, they become a little bit stronger, but not by much. and their strength is well predicted by the black line, which is the prediction by Brandt and Henningsen for the growth of these streaks. And another comment is the streaks remain below the threshold in terms of amplitude for the production of sinuous or varicose instabilities of the streaks. So the streaks want to become, well, in a normal transition in a normal boundary layer, the streaks will either be unstable to varicose instabilities like this, or to sinuous instabilities where the streaks kind of like a snake get thicker or narrower or thicker. And the streaks in this case, because of the favorable pressure gradient, are prevented from doing so. Okay, I think I have to move over this. This is conditional stuff that talks about the mean time between high intensity sweep motions and burst motions. It's very interesting, but a little bit mathematical. This is talking about the probability density function of your Reynolds shear stress generating motions. Also very interesting. The kind of comment, the strong point is that the favorable pressure gradient inhibits the occurrence of strong ejections and strong sweep motions from the boundary layer, which is again more or less the same comment as the streaks are prevented from generating strong wall normal motions. This brings us then to the third region where the flow enters the adverse pressure gradient. What happens in the adverse pressure gradient? Well, the flow enters this adverse pressure gradient with these somewhat diminished streaks still present in the boundary layer. And now the adverse pressure gradient is destabilizing these streaks, and the flow transitions through the kind of instantaneous production of small turbulent spots on the streak. And the generation of these turbulent spots really mimics bypass transition, insofar as we have these streaks that form very rapidly small scale turbulent structures that are hairpin shaped that resemble the types of turbulent structures that you see in a fully developed turbulent boundary layer. They straddle the streaks, and we can see that there's a coincidence with this motions of the streak and the creation of these turbulent spots. But what's major difference between this condition and normal bypass transition is bypass transition is associated with free stream turbulence. And in here, we have no free stream turbulence. All we have are embedded streaks stuck. It's like they were there, not able to do anything, but just waiting to pounce. And as soon as the adverse pressure gradients came, they behave in a manner almost identical as to the case with high free stream turbulence, which maybe leads us to some conclusions that the bypass transition may not be a function of the free stream turbulence or coupling with the boundary layer streaks with the free stream turbulence. Maybe it's simply a instability of the streaks themselves. And the free stream turbulence is just the initial cause of the streaks, and then they can evolve on their own without coupling with the free stream turbulence. Because here we have the streaks growing, getting stuck. It's like we let them grow for a little while, they now stop. And then as they enter into the adverse pressure gradient region, okay, now have your party, and then they behave in a manner very similar to the bypass transition under free stream turbulence. Okay, so maybe a couple of very specific comments. What we see is overall, the breakdown of these low speed streaks in 3D reveals instances of helical instabilities where these streaks, instead of going like this in a sinuous mode or like this in a sinuous mode, they kind of do both, and they more or less helix around in a kind of corkscrew shape. And those helices are secondary perturbations on top of the streak, and they are a consequence, we think, of the interaction between the streaks and natural instabilities that are developing already in the adverse pressure gradient region because of the high destabilization of the boundary layer by the adverse pressure gradient. Okay, to summarize, we have three zones. In the first zone, laminar separation bubble triggers rapid transition through two disturbance amplification modes, one through a Kelvin-Helmholtz inviscid instability, another through a viscous absolute instability that results in the incipient creation of coherent structures and the onset of a turbulence cascade that gets started but then stopped by this favorable pressure gradient region where the strong mean acceleration dampens the structures that were generated upstream, allows the streaks to remain, but inhibits the cross-stream momentum exchange, diminishes the transverse vortical structures, and delays or discourages strong sweep and ejection motions in the turbulence. And as a result, the turbulence is significantly diminished, but the streaks remain. And then in zone 3, where the flow goes into this mild adverse pressure gradient region, the streaks rapidly break down the transition again. So it's kind of a retransition or a re-amplification of disturbances on the embedded streaks, resulting in creation of turbulent spots in a manner that resembles bypass transition, but without free stream turbulence. And we see instances of helical breakdown of those streaks. So these are all very interesting conclusions. I'll leave you with the kind of key takeaways. One of them is the observation of helical breakdown of the streaks in the absence of free stream turbulence, which is very significant because this has never been observed. Prior instances have all been associated with high free stream turbulence levels. So this may be opportunity for more to look at in terms of further study. Thank you very much.
Thank you. Now it's time for questions. Yes, go ahead.
Those are seriously impressive simulations. What sort of computer are you running them on?
This was an in-house or a UBC cluster.
Yeah.
We went the approach of, I just began my professorship and I have no graduate students, but a lot of free time. So I ran it for about 18 months on 96 cores, something like that.
Okay.
How
big is the mesh? How many cells?
Yeah, I forget exactly. I want to say somewhat less than 100 million and more than 50 in that range. I can look it up though.
Okay.
Very cool presentation. Thank you. I was wondering maybe if you can go back because in the sense that we started by talking about the turbines and that usually we use flat plates, right? So after having run this more advanced model, can one somehow couple back and say what the consequence of using the crude flat plate model is, whether it can be improved somehow?
Right. Yes. I think the answer is these flat plate simulations that are idealized without the leading edge are useful for understanding the transition process kind of by itself to make transition models that we then put into RANS codes and use for design purposes. What I did by adding on this additional layer of complication, I don't think violates any of the prior understanding of how transition occurs. What we added on is just additional levels of, well, now this blunt leading edge results in additional laminar separation bubble where we have this inviscid mode, which we understand quite well, coupling with the viscous mode, which we also understand quite well. And so it's not like the whole paradigm has changed. It's just we added in a bunch of extra layers, but those layers behave in a way that is a little bit interesting and unexpected, but not tremendously so because there's still the same physical processes are occurring, just more of them. And so I wouldn't suggest that those who are studying DNS without accounting for the leading edge bluntness are all wrong and what their results are useless. One other comment is I used a relatively bulgy leading edge. The leading edge diameter to length is about, I think 8%. The numbers are here, so one could calculate it, but I forget if it's 8% or 5%. For a low pressure turbine blade, that's kind of thick. More akin to what you would have on a high pressure turbine, which are thicker because there's integral cooling inside of the high pressure turbine. Low pressure turbines generally a little bit thinner. And so it's more sharper of a leading edge. So this was a kind of high stress case that might not be very physically realistic in terms of a real turbine. But on the other hand, turbines aren't flat either. So there's a lot of idealizations that are present in this kind of model. Thank you.
May I ask something before? Looking at these streaks in your discussion, did you have a look at pressure fluctuations? So to maybe connect this performance to pressure fluctuations in the adverse and favorable region?
we did look at them, but they're not nearly as easy to interpret in the context of the turbulence because it's a scalar quantity. And so it's hard for us to understand the interaction between the wall normal velocity fluctuations, the longitudinal velocity fluctuations, their interaction, the shear stresses that are occurring there, and then the pressure term. I mean, if we consider the turbulence kinetic energy transport equation, we understand that pressure strain rate terms are important for the redistribution of momentum into different orientations. And so probably that would be really important here, but maybe it's not so much the pressure as it stands by itself, but the pressure strain rate correlation that we have in the turbulence kinetic energy equation that might be more instructive. There's probably, see, the thing about doing a DNS is you can do it and then retire and you have data to look at for the rest of your career. Yes, very good point.
Okay, yes.
Thank you for this excellent and inspiring presentation. I have maybe a suggestion, not suggestion to interpretation of your energy decay.
Yes.
If you could go to this slide thing, because I think that in this laminar separation bubble, or then if you would do POD analysis on your model, you would find out like structure spanning throughout your geometry. Yes. Which would be mostly two-dimensional. So at the end, I think that the interpretation, I would be really interested for the right-hand side of the picture if you would put a line with slope to omega to -3. Yeah. Because there's a theory for two-dimensional turbulence by Teichmann. Yes. And I think that in this part of the flow, it might kind of explain what you are looking at, maybe a little bit different. That this is local information, so these data should not know about the flow downstream, because it was safe. So the 2D Teichmann turbulence theory, I think it might be different, maybe a little bit more. Sure. Yeah, I mean, I totally agree with you. And if you look at the iso surfaces that we looked at in 3D, we could see quite a bit of two-dimensional kind of structure to that turbulence. So it's a very good suggestion. I think that that's worthwhile to do. Thank you.
One question. Can you comment on your inflow turbulence generation that you use for the simulation?
We have no inflow turbulence. So we have quiescent free stream conditions. Of course, there's truncation errors and other numerical noise that results in fluctuations in the flow upstream of my leading edge. Like in this region, let's say like right here, far upstream of my leading edge, so there's going to be noise there. But the numerical noise is not much larger than machine accurate machine zero. So it's not really what's responsible for triggering the transition process. It's the transition is being triggered by, in my understanding, this interaction between viscous and inviscid instabilities of the laminar separation bubble. So no free stream turbulence, no imposed free stream turbulence. What about on the Zoom? Any questions on the Zoom? Don't see any. No. Okay, I've been standing for an hour. If there's not any more questions.
Let's thank Joshua once again. And that concludes our session.